One of the simplest tests for determining whether a series converges or diverges is called the test for divergence. It's very simple. It says if the limit as n goes to infinity of the an's, the individual terms of the series, if that limit does not equal 0, then the series diverges. In other words, if you're adding up infinitely many terms, the only way that that infinite sum could have a finite value at the end is if the terms that you're adding are getting smaller and smaller and smaller, not just getting smaller, but actually approaching 0. So if the limit of those individual terms either goes to infinity or approaches some other number other than 0, or if that limit doesn't exist at all, then your series cannot converge. A very important thing to note here is the converse is not necessarily true. In other words, if the limit of your terms does equal 0, if your terms are getting smaller and smaller and smaller, it is not necessarily the case that the series will converge. You'll need to do some other test to figure out whether your series converges or diverges. This test is inconclusive when the limit of your terms is equal to 0. Now, the fact is, most of the most interesting series that we're going to deal with do have the property that the limit of the individual terms is equal to 0. So the test for divergence can be helpful, but it's not going to tell you everything you want to know about a series. That's why we have several additional sections of this textbook talking about other tests we can do to figure out whether a series converges or diverges. But this is still a good first step, and we should try this first before doing anything else. Let's look at a few examples. Let's figure out whether the given series converges or diverges. Let's look at the sum as n goes from 1 to infinity of n squared over 3n squared plus 1. Now, you don't have to write out the terms of the series in order to figure this out. But just to make sure that we're clear on what we're talking about, let's at least write out the first few terms. So when n is 1, our first term is going to be 1 squared, which is 1 on top, over 3 times 1 squared plus 1. So 3 plus 1 is 4. 1/4 is our first term. Plus, our next term is going to have 2 squared on top, which is 4, over 3 times 4 plus 1, so that's 13. 4/13. Plus, we're going to have 3 squared on top, that's 9, over 3 times 9 plus 1, that's going to be 28. Plus, what else have we got? Well, 4 squared is 16 over 3 times 16 plus 1, that's 49. Not going to write these anymore because we're just continuing to get fractions with bigger and bigger numerators and denominators. And none of these fractions can be simplified in a neat way, so, we're stuck where they are. But notice that each of these fractions is less than 1, and that seems like that's going to continue. So maybe the sequence of the individual terms will have a limit that's 0, and maybe the series will converge. But let's check that. Let's check, instead of finding the limit of the series, which would be the sum of all these terms, let's just check the limit of the individual terms themselves. The limit, as n goes to infinity, of n squared over 3n squared plus 1. And we can use all the tips and techniques and tools that we have for computing limits to help us solve this. So I'm noting here, I'm looking at this, I'm seeing, well, if n's going to infinity, then the top is going to infinity. N squared goes to infinity, that's infinity on top. And on the bottom, well, 3 times infinity squared plus 1, that's also infinity. This is an indeterminate form. So we cannot conclude, based on the fact that we have infinity over infinity, what the answer is. Remember, infinity over infinity is not 1. Infinity is not a number. So we can't say that this goes to 1, or to 0, or to infinity, or to 12. We don't know. But this is a kind of limit that we're actually very familiar with. We've solved this kind of limit lots of times. In fact, we know there's a shortcut that says you can ignore the lower degree terms on the top and bottom and just look at n squared over 3n squared. And the n's would cancel out, and you end up with 1/3. But let's just do it the better algebraic way, the more rigorous way, just once, just to make sure that we're clear. What we should do is divide the top and bottom by n squared, because n squared is the highest power of n that I see on either the top or the bottom. So let's do that. Let's divide by n squared. Let's take this whole bottom here and divide by n squared. And of course, by dividing the top and bottom by the same thing, we're not changing anything. So we get the limit as n goes to infinity of 1 over, 3n squared plus 1 divided by n squared. That's going to give us 3 plus 1 over n squared. Now, as n goes to infinity, the top is going to 1. The bottom is going to 3 plus 1 over infinity, but of course that is just 0. So we do get 1/3. Now we have to go back and remember what it is we're actually trying to solve here. We found the limit as n goes to infinity of the individual terms, the n squared over 3n squared plus 1. That turns out to be 1/3. But thinking about the test for divergence, what does this tell us about the series? What it tells us is that each of these terms is close to 1/3. And that these terms are getting closer and closer to 1/3 as we go down the line. The further you go, the closer your terms are getting to 1/3. And if you keep on adding up infinitely many copies of numbers that are close to 1/3, what will you get? Well, if I take steps that are 1/3 of a foot every single time, but I do that forever, I'm going to go infinitely far. This series diverges. Since 1/3 is not equal to 0, we know the series diverges. Let's try another example. Let's look at the sum as n goes from 1 to infinity of -6 over n. So we can write out the first few terms here. So -6 over 1 is -6. When n becomes 2, -6 over 2 is -3. So -6 minus 3. When n becomes 3, we have -6 over 3, which is -2. When n becomes 4, we'll have -6 over 4. That's -3 halves. Then we'll have -6 fifths. Then -1, 6 over 6, -6 over 6. Then -6 sevenths. Then -6 eighths, which is 3/4, but I won't bother with that. Then -6 ninths, etc. forever. Let's try and figure out whether this series converges or diverges. So we could try the test for divergence. Let's find the limit as n goes to infinity of the individual terms here. -6 over n. Well, this is actually a very easy limit to solve. The limit as n goes to infinity of -6 over n. Well, that's -6 over infinity. But that's just 0. So in this case, the limit of our individual terms is 0. That makes sense. Looking at the terms that we wrote out, those terms are getting smaller and smaller and smaller. Not just smaller and smaller, but actually approaching 0, genuinely approaching 0. So does that tell us anything about the series, whether the series converges or diverges? No, it does not. The fact that the individual terms go to 0 does not tell us anything about whether the series converges or diverges. This is inconclusive. If we want to figure out whether our series actually converges or diverges, we need to take a different tactic. So here's an idea. The fact is, this series is actually very similar to a series we've already studied. So we can say the sum, as n goes from 1 to infinity, of negative 6 over n. Well, we know we have certain laws about how we can manipulate series. For example, if you can break up a series as a sum of two convergent series, the series will converge. If the series is a constant multiple of another series, that series will essentially have the same behavior as that other series. In this case, every term that we are adding up here has a factor of negative 6, and we can factor those negative 6's out of the entire sum by doing the following, by just saying negative 6 times sum as n goes from 1 to infinity of 1 over n. You can factor that copy of negative 6 out of a finite sum. You can also factor that negative 6 out of an infinite sum. But this series here, we recognize. We've already studied this series, this very, very famous series, sum as n goes from 1 to infinity of 1 over n. That is the harmonic series, which we already know diverges. So because our series is a constant multiple of a divergent series, our series also diverges. So even though the test for divergence didn't tell us anything for this series, we were able to use other facts that we know about the series to determine that it actually diverges. Let's take one more example. Let's have the sum as n goes from 1 to infinity of 3 to the n over 5 to the n minus 1. Now, we could write out the individual terms, but perhaps let's not do that right now. Let's just try the test for divergence. You can see why it's called the test for divergence, because it can identify some series that diverge, but it will never tell you that a series converges, and it won't even identify all series that diverge. Let's take the limit as n goes to infinity of 3 to the n over 5 to the n minus 1. Now, if we go at this naively here and just try to plug infinity in, we're going to get infinity over infinity, because 3 to the infinity power, that's going to be infinity, and 5 to the infinity minus 1 power, well, infinity minus 1 is still infinity. You're still taking 5 to a bigger power. You're going to have infinity over infinity again. But one thing we could do is we could try and manipulate this so that we only have one exponent instead of two exponents here. In fact, let's say the limit as n goes to infinity of, I want to have a 3 to the n minus 1. But in order to have that without changing the function, I also have to multiply by an additional 3 to the 1. So now 3 times 3 to the n minus 1, that's 3 to the n power. And that's over 5 to the n minus 1. And the advantage here is that I could rewrite this here. This is equal to the limit as n goes to infinity of 3 times 3/5 to the n minus 1. because exponents distribute over fractions, and therefore we can pull them out of a fraction as well. Now this we actually can deal with, because this limit, we know what it is. 3/5 is less than 1. In fact, 3/5 is between -1 and 1. If you take that to a higher and higher and higher power, the limit of these individual terms is going to be 0. So again, the test for divergence does not tell us anything when that limit is actually 0. It is inconclusive. Let's erase this test since it was not actually very informative, and let's try something else. In fact, what we should try is just rewriting this expression here using the information we already figured out from our limit. This is equal to the sum as n goes from 1 to infinity of 3 times 3/5 to the n minus 1 power. Well, this is exactly the format that we're familiar with for a geometric series. As a geometric series, remember the format will be the sum as n goes from 1 to infinity of some a, some number, times another number r to the power of n minus 1. And even if you have r to the n or something else written there, you can always rewrite it and kind of rearrange things so that it fits this form exactly. As a geometric series, in particular, with r equal to 3/5, the number that is being raised to the n minus 1 power is 3/5. And since the absolute value of r is equal to 3/5, which is less than 1. Remember, if the absolute value of the r is less than 1, meaning that r is between -1 and 1, the series converges. So here's the point of this whole test and this whole topic here. When you are looking at a new series and you want to figure out whether that series converges or diverges, a lot of the time, the test for divergence is actually not going to tell you much, because a lot of the time you're going to encounter a series where the limit of the terms is 0, and you don't learn anything from that test. But sometimes you do. But the fact is that these limits are usually pretty easy to compute. We're pretty good at computing infinite limits at this point. You can do a lot of these in your head. So my recommendation is this. When you encounter a new series, the first thing you should ask yourself is look at the function that defines the terms, the an function, and say, in your head, what is the limit as n goes to infinity of those terms? Are those terms approaching 0, or are they not? You can figure that out in your head without writing anything down. And if you think, yeah, those terms are approaching 0, then don't bother to do the test for divergence explicitly. Don't bother to write it down, because you've already done it in your head and didn't get anything from it. And you'll have to use a different tool. In the next few weeks, we will learn some new tools, some additional tests for helping us figure out whether a series converges or diverges. Okay. Meanwhile, if you do that limit in your head, the limit of the individual terms, and you don't get 0, if you get a number, or infinity, or total nonsense, and maybe that limit doesn't even exist at all, then you could write that down. Write down the limit that you've just done, and you can conclude right away, immediately, this series diverges, because the limit of my terms was not 0. You can write that down and you're finished. So that's the general rule of thumb. Do this test in your head first.